This is lesson 5-4 notes over nonlinear functions and qualitative and quantitative graphs. So linear functions are all the functions that we've seen up to this point. And when we see a linear function, okay, the function rule is always written in slope-intercept form. So y equals mx plus b. We can write it in that form because it's a straight line. Our slope is going to be the same everywhere. Okay, nonlinear functions are going to be functions whose rates of change or slope are not constant. So those graphs are going to be not straight lines. All right, so like on number 1, it says determine whether the graphs represent linear or nonlinear functions and explain. All right, graphs are simple. The easiest way to figure out if they're linear or nonlinear is literally by looking at them. If it's a straight line, it's linear. If it's not a straight line, it's nonlinear. Now, A is 2 straight lines, all right, but the slope here is going to be -1, and the slope here is +1. So notice, 1, the rates of change are not the same, but also we can just look at it and we know it's not a straight line. So for A, we would say nonlinear, and we would say it's not a straight line. Okay, B, no matter what 2 points we look at, so I could choose this point to this point. Actually, that's not a point on the line, I think. Yeah, that's not a point on the line. Let's see, find another one right here. Yeah, that's tricky. But I could find the slope on any of those points, and the slope is going to be the same. It's a straight line, so we would say that this one is linear, and we would say it's because it's a straight line. And the slope is going to be the same no matter what 2 points you choose to look at on that line. Okay, for this parabola, we would say it is nonlinear. Okay, and again, it's not a straight line. All right, let's look at number 2. Says a square has a side length of s inches. The area of the square is a function of the side length. Graph the function to determine if it is linear or nonlinear and explain. All right, so here in a horizontal table, the top is always going to be x and the bottom is always going to be y. So we're talking about squares. All right, given the side lengths of squares, we need to figure out what the area is. We know that the area is just side squared, or one side times its other side, okay, or length times width. Either way, but with a square, remember all the sides are the same. So it would be 1 times 1 is 1. 2 times 2 is 4. 3 squared is 9. 4 squared is 16. And 5 squared is 25. All right, so then all we have to do is take those points and plot them. All right, like I said, x represents the side length. We can see that in our graph too. The x-axis is the side length. And then y represents the area. The y-axis represents the area. So our points are going to be 1, 1, 2, 4, 3, 9, 4, 16, and 5, 25. Okay, I'm going to plot my points. Notice that the y-axis is going by 2's. So 1, 1 is really going to be right here. Okay, 2, 4 is here. 3, 9 is here. 4, 16, and 5, 25. All right, and then I also know that if I have a square with a 0 side length, 0 times 0 is 0, so I'm going to go ahead and put that point as well. All right, we're going to connect our points. Okay, and you're going to be able to tell that it makes the curved line, and then this would keep going up. Okay, but notice here, our slope is different from point to point. So from here to here, we go up 1 over 1. Okay, from here to here, we go up 3 over 1. From here to here, we go up 5 over 1. Okay, all of those are going to be different slopes, so different rates of change. We would say it's nonlinear for 2 reasons. 1, because the slope or the rates of change are not constant because they are not the same, right? Or for this one, because it's a graph, we can just say the line is not straight in this case. But if we're not looking at a graph, we have to be able to know that the reason it would be a nonlinear function is if the slope is not constant, or if the slope is not the same. All right, which I think we're looking at graphs next. Okay, number 3. Yes, it says, to determine whether a function represented in a table is linear or nonlinear, find the rates of change. If the rate of change is constant, the relationship is linear. If the rate of change is not constant, the relationship is nonlinear. Okay, fairly straightforward. So number 3, determine whether the functions are linear or nonlinear and explain. So if I look at my x values, they are all increasing by the same amount. 1 to 2 is 1, 2 to 3 is 1, 3 to 4 is 1, and 4 to 5 is 1. All right, but over here, my y values are not increasing by the same amount. Okay, so if I want to know an increase from 825 to 1,000, I'm going to do 1,000. I'm going to take the bottom number and subtract the top number. So the difference is 175, and it's positive, which makes sense because 825 plus 175 is 1,000. All right, 1,000 to 1,185 is 185, and I'm actually going to stop there. Okay, so my first slope would be 175 over 1. My second slope would be 185 over 1. Okay, and I can already tell that those rates of change are not the same. They are not going to be constant, so this is nonlinear. But if you needed to, you could check, because sometimes we make errors. So 1,320 minus 1,185 is 135. Okay, so clearly 135 over 1, also not the same. And then 1,320 to 1,420 is 100. So none of those are the same. But honestly, we could have stopped with those first two, and we would say that this is nonlinear because the rates of change aren't constant. Okay, B. All right, 3 to 4 is 1. 9 to 16 is 7. So my first slope would be 7 over 1. Okay, 4 to 5 is 1. 16 to 25 is 9. My second slope would be 9 over 1, and I can already tell that those are going to be nonlinear. So nonlinear. The rates of change aren't constant. Okay, it's for a table. All right, now if we're looking at an equation, it says in order for an equation to represent a linear function, the equation must be able to be written in the form y equals mx plus b, where m represents the slope or constant rate of change, and b represents the y-intercept or initial value. If an equation represents a nonlinear function, two things. One, it will not be written in slope-intercept form, or it might contain one of the following. So exponents other than 1 or 0 on a variable, square or cube roots, or variable expression, so a variable expression within a radical, or variables in the denominator of a fraction. So number 4 says determine whether the equations represent linear or nonlinear functions and explain. Okay, A, I'm going to rewrite this. Y equals x divided by 3 is the same as y equals 1/3 x. And then for B, y equals negative 2x divided by 5. This is the same as negative 2/5 x plus 5. All right, so actually A and B are both written in slope-intercept form. Y equals mx plus b. B would just be 0 here. Y equals mx plus b. So both of these are linear. And we're going to say because they're written as y equals mx plus b. Okay, for C, y equals 3x squared plus 2x plus 5. This is what makes that not a function. And then for D, y equals the square root of 3x plus 5. It's the square root symbol and the fact that that x is underneath the radical. So the x specifically has to be within that radical for it to be not a linear function. So for C and D, there are two things we could write. I'm going to go ahead and write, okay, nonlinear. And I'm going to say they're not, or let's say they can't we'll say they can't be written as y equals mx plus b. You also could have said for C, nonlinear, because the x is squared, and for D you could have said nonlinear because the x is within a radical. All right, but as long as we focus on this, okay, it's linear if it can be written in slope-intercept form. It's nonlinear if it can't be written in slope-intercept form. Okay, and then these are just other examples of nonlinear functions. So they're functions. They would all pass the vertical line test, but if an x is squared, it's going to be this U shape. Okay, if an x is cubed, it's going to look like this. If an x is within a radical, it'll look like this. And then if an x is in the denominator, it's going to look like this. These are all functions you won't see again until next year in algebra, though. All right, so moving on to qualitative and quantitative graphs. All right, so graphs used to represent situations that may not have numerical values are going to be qualitative. Qualitative. Quantitative graphs are graphs that use numerical values to represent situations or relationships. Quantitative. Okay, we're going to focus on this a little bit here in a minute. If we see one of these graphs, these are some of the things that we might see. So it says the rate of change of a qualitative or quantitative graph can show the following. Increasing at a constant rate, decreasing at a constant rate, no change, or just constant. Okay, increasing at a varied rate or decreasing at a varied rate. Now we read a graph from left to right. Okay, so from here, how we read graphs, we typically will say as x is increasing, y, and then we say how y changes. So like, as this one would be as x is increasing, y is increasing. As x is increasing, y is decreasing. Okay, as x is increasing, because again, so these x values, I could put numbers here. We read a graph from left to right. So as x increases, y stays the same. Y doesn't go up, it doesn't go down. It just stays the same. As x is increasing, y increases at a varied rate, or as x is increasing, y decreases at a varied rate. All right, and we'll come back to that as well. Okay, number 5 says answer the following questions about the graph to the right. When is the altitude increasing? Since it says when, okay, that tells us that we're looking for a time. So the altitude is increasing from 0 minutes, it's going up, and then from 5 to 10, it's also going up. So we would say that it's increasing from 0 to 10 minutes. That graph is going up. So 0 to 10 minutes. Okay, altitude is decreasing. So here's our altitude, here's our time. It's going down from 10 to 20 minutes. So we say 10 to 20 minutes. And it says between which time frame is the change in altitude linear? Remember that linear means it's a straight line. So we could say from 5 to 10 minutes and from 10 to 20 minutes. Okay. It says between which time frame is the change in altitude nonlinear? From 0 to 5 minutes. That is not a straight line, it's curved, so we're going to say 0 to 5 minutes. Okay, it says what is the altitude of the helicopter at 10 minutes? Okay, well at 10 minutes, the altitude hits over here, and that's between 4,000 and 6,000, so it would be 5,000 feet. Okay, and then between which 5-minute time period did the altitude of the helicopter increase the most? From here to here, the altitude is going from 0 to 3,000, so 3,000 in that first 5-minute period. And then from 5 to 10 minutes, it's increasing from, it's going from 3,000 up to 5,000, so 2,000 in that second 5-minute period. 3,000 over 5 is more than 2,000 over 5, so we would say from 0 to 5 minutes. Okay, let's look at number 6. It says you can also sketch graphs to represent a situation that's described verbally. So number 6 says Charlie gets on his bike for a short bike ride to his friend's house. He speeds up, rides at a constant rate, and then slows down to a stop. Sketch a qualitative graph to describe the scenario. So since it's a qualitative graph, we don't have to put numbers on our graph. I am going to put a 0 because that corner is always going to be the origin, or 0, and that's helpful for us to remember. Okay, now I'm going to go back to the problem. I'm going to reread all of the things that are happening to speed, because I'm looking at speed over time. So Charlie gets on his bike for a short bike ride to his friend's house. He speeds up. That's the first thing that's happening. He rides at a constant rate. That is the second thing happening. And then he slows down to a stop. That's our third thing happening. Now when he starts, okay, he gets on his bike to ride to his friend's house. So before he started riding his bike, his speed is at 0. So I'm going to start at the origin. Right, then I'm going to draw a couple more graphs. Show you a couple different ways it could look. He speeds up. It doesn't tell us he speeds up, so we know that over time his speed is increasing. But it doesn't tell us if he's speeding up at a constant rate or if he's speeding up at a varied rate, because these are both increasing. So really, this first part could look like this. It could look like this, or it could look like this. Okay? These would probably be the two that are most correct. But any of those would be an increase of speed over a short period of time. Okay? The second thing is that he rides at a constant rate. Now, if he rides at a constant rate, his speed doesn't change. Right? His speed isn't going up, it's not going down, because he's riding at a constant rate. So that's going to be a horizontal line. So something like this. So he rides at a constant rate. It could be for a shorter time. It could just be there. Could be just, it's a short bike ride, so it could be even shorter. Any of those would work. Okay, and then he slows down to a stop. So I would say that when he's slowing down, it's going to be more of a gradual slow down. So something like that would work. Okay, it could be a little bit faster, so it could look like that. Okay, or it could look like something like that. As long as you have an increase, a constant, and a decrease, right, of his speed. So his speed increases, then his speed stays the same, and then his speed goes down when he's slowing to a stop, to where he's back at 0. That's what that graph should look like. Okay, number 7. It says Miss Lopez was driving to school from her home. She was driving on the highway, but then got stuck in traffic, which slowed her down to a complete stop for a short period of time. She was able to start moving again, but at a slower speed until she arrived at school. Sketch a qualitative graph that represents her distance from home related to time. All right, it's qualitative, so again, no numbers. Okay, so distance from home. And time. Time always goes on the x-axis. All right, now, this one is a little tricky because the problem talks a lot about her speed, but really what we're trying to describe is her distance over time. So think about it this way. She started driving to school from her home. So at 0 time, she was at 0 distance from home because that's when she's leaving her house. So I'm going to start at the origin. She started by driving on the highway. It's going to be the first part. She got stuck in traffic, which slowed her down to a complete stop, but for a short period of time. That's 2. Okay, she was then able to start moving again, but at a slower speed until she arrived at school. So really there are 3 things happening again. She's driving on the highway, she gets stuck and is slowed to a stop, and then she's able to start moving again, but at a slower speed until she arrived at school. So what we're going to ask ourselves is what is happening to her distance over time. So for the first part of our time, when she drives on the highway, she's starting at home. Okay, she gets on the highway, all right, and she is going to be covering a lot more distance over that time that she's on the highway. So it could look like this. Okay, it could look like this, or it could look like this, something like that. I think this would probably be the most right. Okay, but then, so that's the first part. Her distance is increasing over that short amount of time, okay, because she's driving away from her home, so her distance from home is getting farther from 0. Okay, now she gets stuck in traffic, right? So her distance from home, if she is stuck in traffic, if she's not moving, her distance isn't increasing, but it's not decreasing either. So for a short time, her distance doesn't change. Okay, it doesn't go up, it doesn't go down. Okay, then her distance continues to increase because she starts moving again, and she's still moving away from home, but she's going at a slower speed. So something like this. It's a slower increase, okay, until she arrives at school. But by the time she arrives at school, her distance from home is going to be farther from zero because she's traveled away from her home. Her distance, she's never getting closer to her home, so her distance from home is never going to decrease. All right, so any of these would be okay. All right, let's move to number 8. Number 8, a plane started down the runway and took off. Within 30 minutes of starting the aircraft, it reached an altitude of 20,000 feet. It then stayed at that altitude for an hour. The plane then descended to 10,000 feet over a 30-minute period of time and stayed at 10,000 feet for 15 minutes before it started to land. The plane took 15 minutes to land. Sketch a quantitative graph that represents the plane's height over time. All right, time. I'm going to do our time in hours. And I'm going to do our height, I'll say altitude, in feet, but this time it says it's a quantitative graph, so we need numbers. So if this is our origin, okay, I'm going to go back up and read the problem to determine the highest altitude that this plane is going to go and the amount of time that I need to put on my x-axis. So it says a plane started down the runway and took off. Within 30 minutes of starting the aircraft, it reached an altitude of 20,000 feet, and it stayed there, and then it descended. So the highest that the plane is going to go is 20,000. So I'm going to come up here, and I'm going to put my 20,000. And then I'm going to go about to the halfway mark, and half between 0 and 20,000 would be my 10,000. Okay, and then I'll go ahead and do 2 in the middle as well. So between 10 and 20,000, I would have 15,000. And between 0 and 10, I would have 5,000. Right, and then I'm going to look at my time. So I know 30 minutes, it reached the altitude, it then stayed there for an hour. So far I've got an hour and a half. Then it descended over another 30-minute time frame, so I'm up to 2 hours. And then it stayed there for 15 minutes, so 2 hours and 15 minutes. And then it took 15 minutes to land, so about 2.5 hours. So I'm going to go to the 3 mark. So here's what I'm going to do. I know I'm going to need, let's see, 30 minutes, an hour and a half, 2 hours, 2.5 hours, 3 hours. That would work. I want to even out my little hash marks, and then I'll just do, let's see, this is going to be 1 hour, 2 hours, and 3 hours. That would work. And then I'm going to do, these will be like every 30 minutes. This will be 30 minutes, an hour and 30 minutes, 2 hours, 2.5 hours, 3 hours. All right, now I'm going to go back up to my problem. See, it started down the runway and took off. So at 0 time, it's taking off. Within 30 minutes of starting the aircraft, it reached an altitude of 20,000 feet. So at the 30-minute mark, I'm going to go ahead and kind of put a little point there. At the 30-minute mark, it's already all the way up to 2,000. So let's see, some type of increase can be gradual or a straight line. Let's see, then that would be my first part. Within 30 minutes, it reached an altitude of 20,000 feet. It stayed at that altitude for an hour, so I'm at the 30-minute mark, so I need to go, an hour would be the next 30-minute mark. So it stays there for an hour. Okay, that would be the second part. The plane then descended to 10,000 feet over a 30-minute period of time. So, and then next, this should be right here. So at the 2-hour mark, it's descended to 10,000. So something like this. Okay, it stayed there for 15 minutes. Stayed at 10,000 feet for 15 minutes. So 15-minute mark would be about here. So it stayed there for a short time. All right, and then it started to land, and it took 15 minutes to land. So at the 15-minute mark would be about 2.5 hours. So then it lands, and it should be at that 2.5 mark, and so it descends. I think that's everything. Let's double check. So within 30 minutes, it's hit 20,000 feet. It then stayed there for an hour. It then descended to 10,000 feet over 30 minutes. It stayed there for 15 minutes, and then it took 15 minutes to land. So yeah, that's what that one should look like. All right, let's look at number 9. Number 9 says Luis is biking to his friend Nathan's house. He gets on his bike and increases his speed at a constant rate for 2 minutes until he reaches a speed of 6 miles per hour. He then decreases his speed at a constant rate for a minute until he reaches a speed of 2 miles per hour. Finally, his speed increases at a varied rate for 3 minutes until he reaches a speed of 8 miles per hour. Complete the graph below to accurately depict Luis's trip. All right, so he gets on his bike and increases his speed at a constant rate for 2 minutes until he reaches a speed of 6 miles per hour. So for 2 minutes, his speed gets up to 6 miles per hour. And it says he increases his speed at a constant rate. Okay, so at a constant rate is going to be just a straight line. And I don't like the way that looks, so I'm going to redo mine. Constant rate would be a straight line. He then decreases his speed at a constant rate for a minute. Okay, so for 1 minute, he decreases his speed until he reaches a speed of 2 miles per hour. So 1 more minute means at 3 minutes he should be at 2 miles per hour. Okay, finally, his speed increases at a varied rate for 3 minutes, so at the 6-minute mark, until he reaches a speed of 8 miles per hour. So at 6-minute mark, he should be up to 8 miles per hour, and it says that he increases at a varied rate, so something like this. It wouldn't be a straight line, it would be a curved line. All right, I believe that's correct. So he gets on his bike, he increases his speed at a constant rate for 2 minutes until he reaches a speed of 6 miles per hour. He then decreases for 1 minute until he reaches a speed of 2 miles per hour, and then he increases his speed at a varied rate for 3 minutes until he reaches a speed of 8 miles per hour. Complete the graph below to accurately depict his trip. That is correct. So this concludes the 5-4 notes.